general relativity, step by step. Now last time I made the observation that a constant vector field had got non-zero derivatives with respect to at least this coordinate system here, this h tan theta business. And I spent a long time getting a bit excited, I think. The fact that the derivatives didn't behave themselves, and we've got this rather complicated term here with a non-zero derivative. Right, well that was a bit of fun, but we need to work out how it does. How does the derivative behave? Well, let's just start out with the vector in contravariant form, and I want to differentiate it with respect to xj. And I'm going to write that as x for a tensor ij, but it's not a tensor. We know it's not a tensor because we've calculated this thing here, and it's 0. At least the example I had was 0 in a Cartesian frame, and the tensor transformation law would imply that it's if it's 0 in one frame, it's 0 in every frame, and that's not the case. So it's not a tensor. So what is it? What is this? What is this thing here? Well, I'm going to answer that. I'm going to see how it transforms. So this is just a notation. It's got an index up here and an index down there, so it looks like a tensor. But it doesn't transform like a tensor, and I'm going to show you why. Well, let's try and transform it and see what the real transformation law is. So x bar ij equals what? Well, that's going to be di v bar I by di x bar j. So what I'm going to do is, instead of taking the derivative with respect to the unbarred coordinate system here, there's no bars here, I'm going to transform the vector itself, and I'm also going to take the differential with respect to the barred coordinate system, which is exactly what I did in the previous screencast and got this rather complicated term here. Okay, so we need two facts here. We need to transform di by di x bar j. What's that equal to? Well, that's di by di x I, di x I by di x bar j. Just transforming the operator. That's transforming the operator. Couldn't start and put anything there, and it still works. And what else do I need? I need to transform the vector itself. V bar I equals what? Actually, I'm getting myself tangled up already. I'm implicitly summing over the vector I, and I shouldn't be, because I'm using I here. So I need to make that a slightly different symbol. We've got an I and a J. I'll call this a K, and of course it's summed over K. I, J, K, and then the next one's going to be L. So how does this vector behave here? It's going to be an L, di x, di x. We've got an L upstairs to sum with an L downstairs. This I is barred, so that I is barred there, and that's completely barred. Okay, so now I'm in a position to calculate what this thing is here in terms of the unbarred coordinate system. Equals. It is di by di x k. Now let me rewrite. I'm getting myself tangled up here. I want to rewrite this as di x k by di x bar j, di by di x k of. You see, all I've done is taken this term here, and I've just written it. I've just swapped those two guys over. It just works out more easily. Have I got that right? Yes, there's a k there. Of this thing here is di by di x bar j of di x bar I by di x L VL, where this thing here is V bar I. So there we go. I've got the differential with respect to x bar j of V bar I. And all I've done is use the tensor transformation law here, and I've effectively used Jacobi's formula here for the total derivative. Alright, well that's great, so let's have a look at it. Now I'm going to use this formula here, which I'm sure you know, u dash v plus u v dash. When you're differentiating a product, you differentiate the first one and leave the second one alone, and then you differentiate the second one and leave the first one alone. I'm actually going to swap over the order, so instead of saying u v dash, I might say v dash u. I might swap the order over, just to warn you about that, because it's easy to make this kind of transformation in your head when you're used to it, and it can be difficult to follow what's going on. Okay, so I've got u v dash equals u dash v plus u v dash, and I'm going to use that formula to differentiate this product here. So what have I got? I've got di v bar I by di x bar j, which is this, equals di x k by di x bar j. Now then, di x bar I by di x L, di VL by di x k. So what have I done there? This operator here, di by di x k, I'm differentiating the v, which is here, and I'm leaving this term on its own. Now, because the product rule here implies I've got to differentiate both terms, oh, and I've just written this kj business here, di x k di x bar j times di 2x bar I by di x k di x L times VL. So what am I doing here? I'm leaving this term alone. That term ends up here. Nope. This term here ends up here. This term I'm differentiating with respect to xk, and of course it's a differential of a differential, so it's a second order differential. It's a bit of a mess. There's all sorts of things going on here. We're summing over the L because it's repeated. We're summing over k because it's repeated. I is free and j is free. Let me write this out, what we've got so far. Let me write out what we've got so far. This is my tensor x bar I j equals di x, I'm just copying that, k by di x bar j, that's that term, times di x bar I by di x L, that's that second term there, times x L k. Because that is the differential of my vector v with contravariant component L with respect to di x k, which is by definition this thing here. Plus this rather peculiar term here, let me just write it out, di x k by di x bar j, di 2x bar I by di x k, di x L, all times VL, and it's summed over L and K here. Okay, this thing here is the tensor transformation law. So if that's all we had, if we just had this term here, I'd say, look, x is a tensor because it transforms like a tensor, and everybody's happy. However, you've got this extra term. Extra, I hesitate to say nightmare term, but, well, it is what it is. It is this term. Look, it's this term here. Here it is. It's just sitting there, making life difficult for you. When I say that Cartesian coordinates are nice and easy and curvilinear coordinates are difficult, messy nightmares, this is why they're difficult. This extra term is a quantification of the difficulty of curvilinear coordinates. My pen's not working. Coords. Okay? And you can see this is a bit of a nightmare. Let me write it out again in slightly more expanded notation. Di x k by di x bar j, di 2x bar I by di x k di x L VL. And I'm going to actually explicitly put the summations in. We've got repeated index L, and what else is repeated? K is repeated. This is a nightmare term from hell. This is a pain. And there's no way around it. This is hard. What you do is you develop notation that kind of puts a fig leaf over this difficult term here. But there's no getting around it. This is hard. But we've got to do it, because if you have a constant vector field, let me find it. It's up here somewhere. Oh, there it is. If you have a constant vector field on a nice flat surface, calculus really ought to work under those circumstances. Okay? This is why it's so hard. This term here, where is it? That term there is why tensor calculus is hard. It's because as soon as you try and differentiate something, you get this nightmare term from hell. But we've got to deal with it, so we're going to deal with it. Okay, I'm going to stop there.